to presenter mode within.
Yep, you're good to go.
Can you see it?
Yep.
Okay. Well, thanks everyone who did sort of signing in. You'll see that the title here is a little bit different than the one shown in Hannah's title slide. And the reason is I think that this is more a more honest description of what I'm actually going to talk about, studying ice-ocean interactions through what I would call data model interactions. Less is learned from Smith Glacier. So because it's a very it's a sort of sector of Antarctica that I'll talk about, but I'll explain I think the meaning will hopefully become clear. Sort of looking at Antarctica at the larger scale, there's been in past years, large contributions to sea level rise coming from the Antarctic ice sheet. And that contribution, that sort of loss of ice that's contributing to sea level, it's not been uniform in time. It's a sort of factor of 3 higher today than it was when we began observing the ice sheet through satellite. And it's not been not been uniform in space either. What you can see when you look at this sort of heat map of thinning rates around Antarctica is that thinning is mostly concentrated around here, what's called the Amundsen sector of West Antarctica. Pine Island Glacier, Thwaites Glacier, and to a lesser extent, Smith Glacier, nestled right in here. And if you sort of read articles in The Guardian often enough, you might have heard of some of these places. So in particular, thinning is going on in the Amundsen embayment. And something that I don't think most people know is that this is, I guess, bad for a number of reasons, but the impact of sea level from ice lost from Antarctica is actually greatest in the North Atlantic. And this is because losing massive amounts of ice from an ice sheet changes gravitation between the ice sheet and the ocean. It changes the way the Earth rotates. So it turns out that ice being lost from Antarctica actually has a larger sea level rise signal in the Northern Hemisphere on UK shores than ice lost from Greenland. So that's something that I don't think quite a lot of people actually appreciate. But this is very relevant to us if we're worried about coastal erosion and other things that result from sea level rise. So why is this loss so extensive in the Amundsen? Well, it's largely because of the ocean. See, around the sort of perimeter of Antarctica in the Antarctic Circumpolar Current, there's waters sort of residing at depth that are warm enough to cause lots of melting to occur. Waters that are still cold, around 2 degrees Celsius, but that's 4 degrees above the melting point for most ocean waters. And in a lot of places around the Antarctic margin, that water doesn't really make it onto the continental shelf because it's crowded out by surface processes, cold water falling from the surface due to sea ice formation. But it turns out that on the Amundsen continental shelf, that warm water has sort of unfettered access to the underside of what are called ice shelves, the floating extensions of the Antarctic ice sheet. Why that's relevant, I'll get to that. We do know that over the past sort of several decades, while we've been observing through via satellite, the ice shelves that are in these places where circumpolar deep water has sort of made its way onto the continental shelf, these ice shelves, these sort of floating sort of awnings that stick out from the ice sheet, have lost a lot of their mass. So I guess, I'm talking about ice loss, ice melting. You would think that sort of addresses the question right there. Warm water getting under the ice shelves and causing them to melt. Well, that's the mass loss done. That's what's causing the sea level rise. That's not actually true because ice shelves themselves, losing mass from ice shelves doesn't contribute much to sea level rise. There's this experiment that's done in some primary school classes. It was done in, what's his name? The previous can't remember, the Inconvenient Truth documentary. Clinton's vice president, I can't think of his name right now. That it was talked about in there as well. The fact that ice that's melting in fresh water, once it melts, it kind of is already displacing the water as ice that it's going to replace. So the level of the water doesn't sort of rise when that ice melts. So in your primary school class, you might have seen this experiment done. Fresh water melting into salt water, fresh ice melting into salt water has a tiny bit of an impact on sea level rise, but it's been sort of calculated to be almost negligible. So ice shelves alone don't cause melting doesn't cause sea level rise. So why is ice shelf melt actually relevant? Well, it's because of this concept known as ice shelf buttressing, something that's been known about even before the satellite era of ice sheet study. The idea is that ice shelves function as a stopgap for ice sheet flow. Here's in these two cartoons, we can kind of see that these ice shelves are sort of, as an extension of the ice sheet, have the ability to grab onto mountain ranges or nunataks or just exposed land or slow-moving ice on either side of the ice shelf, what's referred to as the ice shelf margins, slowing down the ice. And that means that removal of these ice shelves, or even a part of them, can lead to speeding up of this ice. That's what's called ice shelf buttressing, or rather the loss of, that's what's referred to as the loss of ice shelf buttressing. So the loss of this stopgap can cause speeding up of ice from the ice sheet into the ocean. And along with that speeding up, thinning often occurs. You imagine a piece of putty in your hands, when you stretch it, it also gets thinner. Well, that's what happens at the margin of the Antarctic ice sheet when acceleration occurs, especially acceleration as induced by loss of ice shelves. Thinning starts to happen, so that's loss of the ice sheet. And also, if it thins enough, the grounding line, the point at which the ice goes afloat, can start to move inland. So that on its own can cause loss to occur from the ice sheet, but that can be compounded a little bit. So is there potential for even greater rates of ice loss, I guess, in the future after that initial thinning starts to occur? Or, have we already seen that happen? So it turns out that, at least the thought, is that around certain locations on the Antarctic margin, interactions between the ice sheet and topography can lead to something called the marine ice sheet instability. And there's a lot of sort of nuance to it, and I won't go into it, but essentially the idea is that the deeper the ocean is, all else equal, the deeper the ocean is at the point at which the ice sheet goes afloat, the greater the tendency for the ice sheet to move fast into the ocean. And so if something happens, if thinning occurs, if buttressing drops a little bit, and the ice and the grounding line happens to move inland, and this is and it happens, and the ice sheet, and this place where the grounding line retreats happens to be in a sector where the bed deepens inland, as it does over most of the West Antarctic ice sheet, well, then this sort of increases the driving force for ice to be flowing, while at the same time sort of not providing any mechanism to slow the ice down. So if this were to happen sort of again and again, this could lead to some sort of runaway process if buttressing didn't then act to slow it down. And we think that in a lot of cases it might not be able to slow things down enough, and that might be what's leading to these really, really fast rates of loss. So it's important to sort of realize that this marine ice sheet instability, which can potentially be induced by warming oceans, isn't restricted to the Amundsen sector. This area in what's called East Antarctica, Totten Glacier, is a place where thinning is starting to occur. And we know it's occurring as a result of circumpolar deep water coming onto the continental shelf, causing high melt rates in Totten ice shelf. And if this were to turn into some sort of runaway situation, there's a massive part of the Antarctic ice sheet that then can be drawn down and drained, causing lots of sea level rise. Similarly, for the Filchner-Ronne ice shelf, which currently has only cold water beneath it, circumpolar deep water can't really access it. But there's been studies that show drops in sea ice can lead to influx of circumpolar deep water into the Filchner-Ronne, causing high melt rates. And if the Filchner-Ronne ice shelf were to thin by massive amounts, then that would lead to massive amounts of grounded ice loss from this sector, the Weddell sector of the ice sheet, again leading to lots of sea level rise. So it is something to be aware of, it's something to understand, and it's something to study. So this is the part that Hannah mentioned where there's going to be a poll. So I teach a class in an undergraduate geography class called Ice and Climate. And I talked to them for much longer than I talked to you, showing many more figures about ice-ocean interactions and how ice sheets respond to ice shelf thinning and how it plays out. I haven't given you the background that they have, but there's no harm to making a guess. So this is going to lead into a poll, and I'm going to explain what I'm actually asking. Considering 3 different scenarios. Now, I'm using a numerical model to evolve an ice sheet and an ice shelf in response to ice shelf melting. They're very idealized. This isn't just, it's not scientific rigor that I'm after here, but all the equations that describe the dynamics of ice sheets and ice shelves are in here. And I want to know how they respond in different scenarios. And I'll describe those scenarios. In one, the ice shelf is essentially unconfined because it's very wide. So there is very little buttressing. The ice shelf might be grabbing onto its sides, but it's so wide that the buttressing essentially doesn't matter in this case. In another case, in the center and right cases, the ice shelves are very confined, and so there is a lot of buttressing going on. In the first 2 cases, the ice sheet is sitting on a bedrock that shallows inland. In the third case, it's sitting on a bedrock that deepens inland. What I'm going to do in the movies that come on the next slide is, basically all these ice shelves are being exposed to parametrized melt rates, not a real ocean model. I'm going to sort of kick up that melt rate, and I want you to try to decide in which of these 3 scenarios does ice sheet retreat? Does the ice sheet sort of strongly retreat when melting is increased? So that's left, where the bedrock shallows inland and there's no buttressing. Center, where the bedrock shallows inland and there's lots of buttressing. And right, where the bedrock deepens inland and there's lots of buttressing. I think Hannah will just stop the poll.
Yeah, we'll give everyone just a little bit more time to look at these images and vote. If you're joining us on YouTube, feel free to put in the chat what you think the answer is going to be. There's a few more seconds for people to vote, so choose one of those 3 options.
This is really just to grab your attention. And as I said, I usually show this to students after I've talked with them for an hour, and that's following other lectures where I've talked about similar concepts. Okay, so the most votes went to the right, but I guess people can also, you could have guessed left and center if you wanted. So let's see what actually does happen. So at time 0, melt rates increase, and the ice shelves all start to thin. In only one of the cases, the right-hand side, do we see extensive retreat of the actual grounding line. So I'm going to sort of try to break that down a bit. I want to look at the center case first. what's happening is the ice shelf is starting to thin. It's losing its ability to buttress. So even though you can't see it, the ice upstream, the ice sheet upstream is starting to flow faster, and it's starting to thin. And eventually, if you look very closely, you can see ungrounding starting to occur. It's starting to thin enough that it's going afloat. When that happens, the grounding line is moving inland a bit. But when the grounding line moves inland, and it's now in a location where the ice is not as thick, the grounding line is not as deep, the driving stress to make it sort of flow faster is sort of decreasing at the same time as the buttressing, which is sort of preventing that flow, is decreasing. There's scope for this to become stable because in its new steady state, again, the buttressing is just enough to prevent the ice shelf from flowing, even though the buttressing has decreased. In the left-hand one, there is no buttressing initially. So the only thing playing a role, there's basically, the ice shelf is playing no dynamic role in the evolution of the ice sheet. And that means when we take it away, it still plays no role. There was really nothing to lose. So thinning the ice shelf doesn't cause anything to happen. In the right-hand side, the ice shelf is thinning. And when the ice shelf thins, just as in the sort of center column, the grounding line moves back. But when the grounding line moves back, it would actually require even more buttressing than before to be in a steady state. Rather, it's getting less buttressing. And that gap between how much it needs to be in a steady state and how much it's actually getting is diverging constantly. And that's why the right-hand column is the only one in which there's substantial retreat of the grounding line. And that seems pretty dramatic, but look at the time scale. We're talking, hundreds, we're talking centuries before anything noticeable actually happens. So these are long time. So we want to be able to understand this in real settings, but we also have to keep in mind that these time scales are perhaps much longer than anything we've been observing. And we might not be able to sort of test out models that make predictions. We might need to sort of resort to other things. So, as I said, we want to be able to know what these ice sheets are, what the Antarctic Ice Sheet and I guess Greenland Ice Sheet as well are going to do. We want to know how they're going to behave in the future in response to climate change. In response to basically nothing. How will they behave if climate change were to just stop tomorrow? We want to know this because for purposes of planning, of mitigation, I would say for adaptation. Mitigation, perhaps, if we think that mitigation of, CO2 going to the atmosphere will reverse any of these processes, but we can't sort of understand, what we should be doing without having some idea of how this ice sheet is going to evolve under future scenarios. And we're sort of like looking at very long time scales. So we kind of have to use numerical models to even get our head around what's going to happen in the future under different sort of climate change scenarios. And ice sheet models, present a possible way to do this, not a definite way. They have evolved over the past, several years, several decades to include many, but I wouldn't say all, physical processes that are relevant to ice loss. So one might ask, how are these ice sheet models that, lots of different groups across the world are spending a lot of time developing, how are they actually doing? The answer is not great. Because when you have physical systems that evolve over such long time scales, one of the only ways to sort of to compare how the performance of different models is with what are called model intercomparison projects. This is one that was published recently about the INITMIP model intercomparison project. Basically, this intercomparison took this sort of leading Antarctic ice sheet models from around the world and asked them to initialize their model as, however they liked, to some representation of the current state of Antarctica. And then they took all of these models and then forced them. By forcing, I mean they sort of applied some representation of marine melting to their ice shelves, and then saw how they responded. So in the first experiment, there was sort of no, it is in the first experiment, which was sort of the no change, no climate change, no change to current conditions. The experiment compared how these different models behaved, over 100 years, which is quite a long time. And there was quite a lot of variation. There were some models that led to sea level drop, others that led to sea level rise, but how much was highly variable. And also, the response to marine forcing was really, really variable as well, like as variable as it can be. So this kind of suggests that we don't have our heads wrapped around how to initialize our models of ice sheet behavior just yet. And one of the things, I guess something that I'll talk about a little while later, is that the spread of these projections can be attributed in part to the way in which modern data was assimilated into these ice sheet models. So we kind of come to an important question. How is Antarctic ice loss likely to evolve in response to climate change over the next century? The challenge there, then, is that current Antarctic ice sheet models struggle to capture the dynamic state of the actual ice sheet, which raises questions regarding predictions using those models. And that's kind of what I like to focus on. So in the rest of this talk, I'm gonna talk about my own research aims. When I was talking to Hannah about what I should include in this talk and how it should proceed, she said, well, people just want to know what you're working on. So I'm going to talk about what I'm working on. And so for that reason, there aren't going to be a lot of pictures of photos of penguins and icebergs in this talk. Not going to be a lot of clever analogies. I'm just going to talk about what I'm interested in and what I do. And what I want to do is to address some of these challenges by developing methodologies, because that's what I like to do. Methodologies for improving the way we model the Antarctic ice sheet, or sections of the ice sheet at least. And one way is by incorporating a wider set of observations into ice sheet initialization than has been done before. And I'd like to sort of extend those methods to ice sheet, to models of not just ice sheet dynamics, but coupling between ice sheet dynamics and ocean circulation in order to constrain the impacts of ocean and climate change on Antarctic ice loss. And I'd also like to be able to attempt to constrain the uncertainties that arise from these. So I'll kind of talk about these different aims and how they kind of work their way into studies that I've done basically since being in Edinburgh. So that's a brief overview of the rest of the talk. And I'm going to try to keep it to 40 minutes, or at least 45, and I think that's doable. I'll give a brief overview of what I mean by ice sheet model initialization, which is sometimes called assimilation or calibration. And that kind of maybe explains why I chose the title I did. Model data interactions is kind of another word for assimilation of data into models. I'll talk about my study area, which isn't the entire Antarctic ice sheet, because that's I think we lose something by trying to sort of model something globally when we can identify problems by looking at really kind of smaller sectors. Talk about what I've done in the past to try to improve ice sheet initialization and coupled modeling, and what I'm kind of trying to do now to improve the initialization of these coupled ice ocean models and uncertainties within. So apologies, because this is going to get a bit mathy, but I won't stay on it for too long. How do we actually implement assimilation? This is just an example of assimilation within a sector of the Antarctic ice sheet. This is Amory Ice Shelf in East Antarctica. You can barely tell the difference between the observed speed and modeled speed, and that's because of a kind of complicated numerical process that we've implemented here in Edinburgh, but other people do as well. So how do we actually do this? Well, ice sheet flow, this is just a little bit about the sort of physics of what goes on within an ice sheet, or at least a fast-moving ice sheet. Ice sheet flow is determined by the drag, the shear stress that's being imposed due to interactions with the bed at the bottom, and internal deformation. And there are parameters, that's what we usually call them, parameters within the model, which govern how these processes sort of operate, but they're difficult to observe directly. And there could be many, many of these parameters because they could vary spatially or spatiotemporally. These parameters need to be calibrated with observations, and the methods are complicated. So without sort of, I'll use a bit of maybe an analogy, an analog, I guess, of linear regression. Now, linear regression is something that I think most, if not all of you, have come across before. But if we break it down, it's not too different than more complex methods of assimilation. We've got a model, which is y equals ax plus b, the model for a line. We've got the parameters a and b, and we've got a way of sort of expressing the misfit between the model and the data. And by minimizing this, we find our optimal values for our parameters. We do the same for ice sheet models, but the differences are that there are tens or hundreds of thousands of parameters, and the Ford model is not y equals ax plus b. It's very, very complicated and often needs a supercomputer to solve. And so is this gradient. So in most efforts, I mean, this is so difficult to do that in most efforts, the Ford model is not time dependent. It's not evolving. It's just it finds velocity as a result of these parameters and the bathymetry and geometry of the ice sheet at a single point in time. It doesn't incorporate what we've seen, for instance, over the last 10 years or the last 30 years with respect to ice sheet thinning. And so this is often called a snapshot projection, a snapshot calibration. I think projection is the wrong word. A snapshot calibration is basically taking into account what's going on right now, but not taking trends into account. And this is what is, for the most part, done. Now, before I talk about that first point of what happens if we try to sort of instill trends into ice sheet models rather than just looking at snapshots, I want to talk about my study area. Smith Glacier is kind of a small section of the Amundsen sector. My cursor keeps on doing weird things. We've got Pine Island, the big ones, Pine Island and Thwaites, and then we've got this small one, Smith Glacier. But it's thinning, it's the fastest thinning of the three. It's got strongly melting ice shelves. Sorry, it's not advanced yet. It's relatively small compared to Pine Island and Thwaites, but it's responsible for 1/6 of all the observed Antarctic mass loss. It's small in size, it's in a highly dynamic state, and it's strongly coupled with the ocean. And for that reason, I decided, I guess years ago, that it makes an ideal test site for new methods, because new methods often require a lot of experimentation, and that requires a bit of a smaller domain, but can maybe provide lessons that can be extrapolated to larger areas of the Antarctic ice sheet, or lessons that can be carried over to modeling studies over larger areas. So as I said, there's this notion of snapshot calibration, just taking in observed velocities. And well, what I thought, what if we could also incorporate somehow the trend, the thinning trend of an ice sheet into its calibration? What impact would that have? And would it look any more reasonable. So out of this study, I guess the results here was that calibration of an ice sheet model to a snapshot of velocity alone definitely does not correctly initialize the dynamic state. Transient calibration might, but I think more work is necessary to determine if that is truly giving us, better calibrations that optimize forecasts. But it seems like it might be in the right direction. So for this study, when I sort of developed a way to try to incorporate thinning rates as well as velocities, I just decided, I guess for fun, to see what happens if I kept on running that model without applying, imagining that there was no further thinning, no further thinning due to melting of the ice shelves, no further warming of water, just kind of as it were. What happens if that, I guess, what is the inertia of that ice retreat? And it turned out to be, significant, but slowing over time. So in these images here are showing, where ice is, where the coloring has gone away. That's where the ice has retreated and gone afloat. Where there's blue shading, that's how much cumulative thinning has taken place. And we can see over the next, the calibration stopped at 2011. Over the next 30 years, there was a retreat of the grounding line, but it kind of slowed over time. And so this kind of begged the question. So how does, if this new ice shelf cavity, which was being formed by ice going afloat, were allowing ocean to come in and sort of influence melting, how would that change this whole picture? Would that lead to a runaway process of marine instability? Would it lead to slightly more thinning? Would it lead to basically about the same amount of thinning and retreat? Well, to do that, I needed to understand ocean circulation under these ice shelves, within these ice shelf cavities a bit better. So I think before this study was done in 2019, not too much modeling of the ocean circulation under these ice shelves, dots and ice shelf and cross and ice shelf, had actually been done. I guess because they're kind of small, they take a second stage to Thwaites and Pine Island, and there wasn't much attention being paid to them. But my colleague Noel Gormlin, who processes high-resolution satellite altimetry, was able to observe patterns of melt rate under dots and across an ice shelf. We can see, and we were able to see that there were sort of distinct patterns of elevated melt in some places, much higher than other places. And it seemed to be, well, it was interesting what was leading to those patterns, but it also sort of prompts the question, if an ocean model cannot represent those patterns, how can we hope for a coupled ice ocean model to represent the evolution of ice sheets in response to climate change and ocean warming? Well, so the main result of this study was that the bathymetry that we use in our ocean models underneath the ice shelves is very, very critical. The sort of up-to-date product at that time, our topo, didn't really resolve the bathymetry under these ice shelves very well. And as a result, the melting, the sort of modeled melting from the ocean model looked not very good. If we used when we used an aerogravity product, a product of ice shelf bathymetry developed using aerogravity, things improved a bit. There's not an exact match between this pattern and this pattern, but it looks a bit closer. And there were other things that could be done to make it look sort of even better in certain places. I guess the idea here, or I guess the main result here, was that bathymetry is very important. But another thing that came out of this is that how accurately we model melt rate under an ice shelf depends on where under the ice shelf we are, if what we care about is loss of buttressing. So this is kind of a heat map, not of melting, but of sensitivity of the grounded ice to melt. What it's showing is that under large areas of the ice shelf, there's not much sensitive, as in melting in that location won't do much to buttressing. This big sort of melt channel making its way under Dotson, there's a lot of melt going on under there, but it doesn't seem to be doing that much to buttressing. Melting at the margin between Crossan Ice Shelf and Dotson Ice Shelf, where they kind of fuse together, that has a lot of impact. Melting in the margins of Crossan Ice Shelf has a lot of impact. Melting near the grounding lines has a lot of impact. So it kind of, it really states how complex this whole system is. In order to understand grounded ice, like how much ice loss is going to occur from different parts of the Antarctic ice sheet, we need an ocean model that accurately represents melt rate. We need an ice shelf model that sort of accurately that represents these sensitivities, and we need an ice sheet model that equivalently sort of responds to buttressing in this sort of specific way. So I guess it's showing that this whole system is quite complex. So the next step in this kind of, I guess, series of studies was to address that question of what happens to Smith Glacier over time, over several decades, if the ocean circulation is allowed to evolve freely under this growing ice shelf cavity. And for that, I needed a coupled ice sheet ocean model. And I mean, those kind of exist elsewhere, but I'd like to think that this one was a little bit better because it sort of lets the ocean evolve freely, and it sort of lets the ice cavity evolve, sort of the ocean evolve as the ice cavity evolves. They sort of co-evolve with each other. So in this kind of, these images don't really do it justice, but what I'm using here is a framework that lets the ocean circulate under an ice shelf, cause thinning to occur, and when that thinning occurs, the ocean sort of like neatly moves up to sort of fill in that void. And there's no sort of discontinuities or stopping and restarting of the model. And it made things it just made things a lot cleaner. But I guess that's just to emphasize that I'm using a fully coupled ice ocean model to the next stage of the study. And it's within what's called the MIT General Circulation Model, MIT-GCM. Some of the people tuned in might engage in ocean modeling, even those that don't might know of or might use MIT-GCM. It's used a lot for global ocean studies. It's also used a lot for sort of focused regional studies. And that's the sort of the way in which I'm using it. It's got an ice sheet model in it. It's got a sort of model of ice-ocean interactions. And so that's kind of what I'm using for the study that comes after this. So the issue, though, is that if I'm going to take this coupled ice-ocean model and apply it to what I hope is something realistic, it must be initialized in a highly dynamic state. I realize it's 1:42. I'm going to try to hurry. The challenge with transient with initialization is that, well, coupled ice-ocean modeling is really in its infancy. And a lot of studies that have been done are sort of like really highly idealized. They don't kind of address this question of, what happens if we apply this coupled ice-ocean model to a very dynamic, to an ice sheet that's at this moment very dynamic. The potential issues here are that if an ice sheet is sort of responding, like if an ice sheet model kind of immediately has to respond to an ocean model that's melting it, but it's not been initialized in the right way, it might still be adjusting in response to that initialization. That might be the bigger factor that's controlling it. This could lead to a change in the ice shelf cavity that in geometry that's not realistic, causing the ocean model to do non-realistic things, which would then feed back on the ice model, causing it to do more non-realistic things. I guess the emphasis here is that these are two sort of components of modeling the climate that are, moderately understood at best. And then there's interactions between the two that we don't really understand yet. So it's really important, in my opinion, when this is done, to try to get the ice and the ocean system sort of as in balance with each other, and as sort of, and to respect as possible, and to respect the sort of like the transient evolution, the trends inherent within the actual physical system as much as possible. So without going into it too much, that's what I tried to, within this coupling, within this sort of methodology that I'm using now, I tried to have a way to do that a little bit better than, I guess, than the simplest thing to do, which is just to do a snapshot calibration and stick an ocean model underneath it. So this coupled ice sheet model it integrates observations of thinning and speed, and it's kind of in balance with the ocean model rather than responding to its initialization. So just I'll go quickly through this because I know I need time. I initialized a coupled model using just a very sort of small sector of the Antarctic ice sheet, using boundary conditions downscaled from a larger ocean model run, and ensuring that the melt rate was consistent with cryostat observations. The ice model is using what's called the bed machine bathymetry and initial thickness products, and it's using surface mass balance. Basically, its interaction with the atmosphere is coming from model output, but validated model output. And there's two possible ways in which I ran this. One, in which I just did a snapshot calibration and stuck an ocean model underneath it and let it go. And we can see that the inherent trend of mass loss within the ice sheet, especially where mass loss, where thinning is large, is not in agreement with observations. But when I calibrate the ice model transiently, sort of taking account of the ocean melting as well, I do get a solution that looks a lot more like, reality over the years 2011 to 2015. So what happens when I sort of like initially start running this model is that the grounded volume loss rate between the two, between these two simulations, is offset a bit. This VAF is kind of important, so I'll just describe it quickly. Volume above flotation is basically the volume of ice within an ice sheet that can still contribute to sea level rise. That means if an ice sheet sort of goes afloat, it's lost its volume above flotation. Until then, it's contributing to sea level rise. So in both of these simulations, the snapshot and a transient calibrated one, the mass loss rate is about 20 cubic kilometers per year, which is close to observations. The offset is because the transient one was calibrated using observed thinning rates. The snapshot one was not. But they're both responding to the ocean. They're both responding to seasonal changes in melt rate, and we can see this sort of variation over the year of the seasonal cycle. It's actually quite large, but the offset is due to the calibration. There's no divergence in the sort of pattern of melt rates because 4 years is not long enough for the cavity geometries to diverge. But over the longer term, they behave quite differently. This is a 50-year simulation of volume above flotation between the two. And what we see is that basically, I guess I'll just get right to it. Essentially, the transient model, the snapshot calibrated model is just lagging the transient model, meaning I believe this is the trajectory that the ice model wants to take. This difference here in rates, in trend of mass loss, is initialization shock. And that shock goes away over about 20 years. Now, if we're running this model for 500 years or 1,000 years, that's negligible. I don't think we care about that. But no one's going to be around in 1,000 years. No one's going to be around, especially no one can check our projections. If we're trying to make projections for 30, 40, 50, 60 years into the future, then I think we do care about this error plus minus 10 to 20 years or so. You can also see, just to quickly point this out, in this transient run, the VAF dips a little bit, about 35 years. That's because the grounding line kind of went over a sort of a small deepening in the bed. But then that deepening kind of recovers, and that's why the rates of loss have sort of slowed a bit. So that's kind of, this marine instability is a real thing, but it's sort of limited to sort of like local patterns in the bedrock. I like to show a movie because I think it's nice to show how we really do need coupled models, coupled ice ocean models, to predict what the ice is going to do. So this is a transect at, well, I guess it's just kind of showing cross an ice shelf, dots an ice shelf. I plotted, over time, the transect of ocean temperature, ocean temperature along that transect. And that's what this movie is showing. I'll go back. What we can see is that the temperature within this little, sort of canyon here, initially, because the ice is so thick, it's not that warm. Not enough circumpolar deep waters is able to access this bit. Over time, as the ocean cavity changes in very complex ways, more warm water actually can get into this deepening bit and cause higher melting to occur sort of further up in the ice shelf. And I think that's a sort of non-trivial way in which, in which the ice and the ocean can interact. The ice shelf cavity changes, allowing new pathways for circumpolar deep water to cause melting. So I just wanted to see how bad things could get. So I took, instead of having a seasonal cycle in oceanic boundary conditions, I just kept oceanic boundary conditions frozen in the sort of like deep summer state in a very warm year. And so in that sense, this is basically melting here was as large as it could have possibly gotten. Volume of flotation dipped way, way down to 40 meters per year, but then sort of recovered. So still, I didn't see any sort of long-term marine instability. And I guess something to note is that the melt rate falls as the glacier retreats and the grounded mass slows. The grounded mass loss slows as in other experiments. So in all these experiments, I'm not seeing anything like complete marine ice sheet instability. I'm seeing interesting behavior, but I'm not sure that this is at least over the next 50 years, has the potential for marine instability. It could be that, farther on into the future, things could happen. So the results of this sort of study that I just showed is that even under extreme scenarios, marine instability of the Smith Glacier is not observed over the sort of 50-year timescale. What I also found was that the choice of the initialization methodology, and this is relevant to a lot of other studies that are looking at coupled ice ocean phenomena, it seems to introduce uncertainty of around 15 to 20 years in predictions, but not complete divergence of these trajectories. So, on a longer timescale, that might be fine to do. But Smith might be inherently stable, and it might be that other catchments like Pine Island Glacier, Thwaites Glacier, Totten Glacier are inherently unstable, meaning that the choice of initialization methodology probably matters quite a lot more, even for the 100 to 500 year timescales. And what have I learned about methodology is that coupled transient initialization, which is what I'm calling it, it requires a really high fidelity ocean melt model. And we need to improve models of ocean cavity circulation. And we also don't know what the uncertainty associated with the initialization actually is. Can it be quantified? How does it affect projections? And that, I guess, I'm almost done, but I want to, say a bit about what I'm doing now. I'm applying, as Hannah mentioned, I'm part of the International Thwaites Glacier Collaboration, Project Profit. And the aim is to look at projections over the next 100 years or so of the entire Amundsen, Thwaites, but really Pine Island and Thwaites and Smith. So this methodology is now being sort of, scaled up to look at the entire Amundsen sector, methodology that I just introduced. It'll take longer to run, more computer nodes will be needed, but hopefully we'll discover some interesting things and learn a bit more about what is needed for initialization of these projections and how that impacts the projections. I mentioned that we need to improve our ocean modeling, and I mentioned how we need to know the bathymetry of within these ocean bathymetry under these ice shelf cavities a lot better. So a recent study I did look at this. It didn't look at how to improve this characterization of the bathymetry, but it looked at how to find where the bathymetry actually does matter to melt rates. And it turns out that even though, for a long time we didn't know much about the bathymetry under Dotson ice shelf, turns out there's only a few places where we actually might need to know in really high to very high accuracy what the bathymetry is under Dotson ice shelf. So that might help guide our sort of future geophysical investigations and that serve to improve ocean modeling, I hope. And just lastly, these, to quantify the impacts of uncertainty, of initialization uncertainty, it basically requires understanding how this sort of like large-scale optimization actually depends on uncertainties of the observations, and how that allocates uncertainties to these, tens or hundreds of thousands of parameters, and how they impact what the initialization, how they impact projections with the ice sheet model. So again, that's kind of that's something that's in its early days as part of this project Quorum, but I think there's been good results again looking at Smith Glacier. So with that I'll close. I'm sorry I meant to take 10 minutes less. I apologize for that. I'll close with finally a picture of an iceberg. I was on a cruise in the Weddell Sea 16 years ago now, and I was on the and that was the last time. That's the only time I've ever done polar field work. So I know that's disappointing for people giving polar talks. I'm sorry. I was on the deck of the ship and I saw this really, really strange looking iceberg. Don't know how it came to be shaped like that. And just then the ship sort of pulled away from it. So I guess we'll never know, but I just kind of like it. Thank you very much for your time.
Thank you, Dan, for that talk. That was crammed full of information. I'm sure that actually the content that you've just discussed today actually happens over a series of lecturers for your undergraduates. But thank you for providing today's MASTS webinar. We've had a couple of questions in already in the Q&A box. So for our audience who are with us right now, then please use the live chat if you're joining us on YouTube to submit a question, or use the Q&A box that is at the bottom of your screen to submit a question to Dan. And we're going to work through those in just a second. Just a reminder that this entire session is being recorded. So if you aren't able to join us or want to recap on anything that Dan has mentioned today, then please check out the MASTS YouTube channel where you'll be able to find a recording of this session. So I'm going to move to the first question that we have in the Q&A box on our screen, Dan. And that is from Matt. It came in straight after you started talking, actually. So it's quite a general question, but with your expertise on the topic, Matt is asking, how worried should we be about disintegrating ice shelves and melting ice sheets in the future? How long do we have to even prevent, if possible, ice loss under different climate scenarios? So that's quite a big, broad question, but with what you know, how do you answer that?
Well, I would answer the first question. How worried should we be about disintegrating ice shelves and melting ice sheets in the future? I would say maybe less worried than we should be about the next superbug, and less worried than we should be about weather variability leading to increased, superstorms, hurricane damage, things like that. I honestly do think that there are bigger threats to the climate, but I guess there is a fact that when sea level rise occurs, it is permanent. Yeah. So disintegrating ice shelves, that seems to be happening. It's happened in the past in the Antarctic Peninsula. It's kind of working its way down. Larsen Ice Shelf is the next one that might go, but even when Larsen Ice Shelf completely fails, there's not massive ice streams flowing into it. So I think it will be, my guess is it will be very, like many centuries before we start seeing, melt ponds with the extent that we've seen on the Larsen Ice Shelves happening on, Fulton-Arani and the Ross Ice Shelf. So I think there's probably bigger threats than disintegrating ice shelves in the future. How long do we have to prevent permanent ice loss under different climate scenarios? Well, there's a question as to whether the ice loss that we're seeing from the Amundsen embayment, which is sort of the point at which there's the most ice loss coming from Antarctica. There's a question of whether that is because of human-induced climate change. And if it isn't, well, then probably we might not be able to prevent it at all.
Understood. Yeah, I was just going to comment on something that you said right at the beginning of your talk, that actually the melting ice loss in the polar region isn't as it impacts the waters nearer us than it is the ice melting in Greenland, which was something that I kind of learned about this week, and I thought that was really interesting, that actually melting ice in different locations has not the impact that you think it's going to. But moving on to Matt's next question, which is something I've not actually heard about.
Neither have I.
Yeah, they just for reference for anyone who's listening, Matt is asking what are your thoughts on proposals to enhance sea ice albedo with white silica sand, or build barriers to limit caving as a measure, or to preserve ice shelves. So I hadn't really heard of this white sand tactic.
I can't say anything on. I would need to think about that, because it's the first I've heard about enhancing sea ice albedo with white silica sand. All I would know is, all I can say, that would require a lot of sand. There's something like, several 100,000 square kilometers of sea ice appears every year, and then a lot of it melts, and then we wouldn't get the sand back. So indeed. I think that would be expensive. So could we build barriers to limit calving as a measure to preserve the ice shelves? I haven't heard any talk about building barriers to limit calving. I've heard of an idea, and I kind of suspected someone was going to ask about this. Can we build a barrier to prevent circumpolar deep water from making it? I should share my screen now. That's all right. No, I am sharing, aren't I?
You are, yep.
Okay, so there was a paper with this kind of like a little bit off the wall idea that came out a few years ago, with the idea that a big seawall should be built in front of Pine Island Glacier, about yay high. That would prevent the warmest of the waters, even in years in which the thermocline was moving up a bit, from making its way under Pine Island Glacier, because this sort of mount itself does prevent Pine Island Glacier in at least cooler years from melting strongly. I guess the idea is to build another, barrier here, which would cost something like, 10 trillion pounds. I think someone did a more recent study on this, showing that when that happens, well, the reason that I think one of the reasons that Thwaites Glacier and Smith Glacier melt a little bit less than Pine Island Glacier is that when water makes its way onto the onto the continental ice shelf in front of the Amundsen. This is taking for ages, sorry. Well, the circumpolar deep water sun kind of takes a lap around the continental shelf. First stop, Pine Island. So if you prevent warm water from going under Pine Island, then the circumpolar deep water that sort of made its way around to Thwaites and Smith is going to be a little bit warmer. And I haven't read the paper, but I think someone did do a study kind of showing that if you were to prevent melting from one ice shelf, then it would lead to higher melting in other ice shelves. So I don't think building a seawall to prevent melting is a great idea. And the sea ice albedo idea I hadn't heard about, but it seems, I don't know, I'd have to think more about that. Tamsin asks, what are your plans for quorum? Or is there a web page I can find the info? Well, Tamsin, I think maybe we can email a bit about this. It's because I don't want to get too technical or bore too many other people. The plan is kind of a little bit in the air because we had a postdoc go take a job in industry. But if you're okay with it, I can just send you an email sometime.
Dan, I think you have your contact details on your final slide actually, which might be helpful for anyone who wants to follow up with you.
I know Tamsin's email, so I can.
Okay, that's fine.
I don't have a proper web page for it yet, Tamsin, but I will definitely email you.
Yeah. The next question is from Nick, asking evidence of the way that the last British-Irish ice sheet decayed and sea level rise is often promoted as giving potential analogies for the future of Antarctic ice. Do you have any perspectives on this, and are you aware of such evidence feeding into the field of your study?
So paleo evidence, it does seem to provide a measure of what things are going to happen. But, and I've definitely seen, British ice sheet, the British ice sheet decay talked about as an analog for the future of the Antarctic ice sheet. I've seen kind of evidence of past retreat of the Antarctic ice sheet. Looked at as a sort of an analog for what's going to happen with the Antarctic ice sheet. I think perhaps paleo evidence of the Antarctic ice sheet and how it's retreated in the past might play a stronger sort of, might be a better analog. But it's hard to say exactly, it's hard to say exactly how those are going to help quantitative predictions. I mean, the fact that the Amundsen margin has retreated from the edge of the continental shelf to where it is now in the past, and the fact that it's, we kind of know how long it's taken to do so, does give us a little bit of information as to what the ice sheet is capable of. And it kind of gives us timescales, but timescales on the order, with granularity of maybe centuries. And I think that is important to understanding what might happen in the next few centuries with the Antarctic ice sheet. I guess it's difficult to take, something, proxies with plus minus 100 or 1,000 years sort of dating accuracy, and use that to say what's going to happen. Like, you may get use out of that for making a prediction over what's going to happen in the next 50 years. And I think it's important to sort of remember the distinction between these long timescale predictions, which we won't be around to see and test, and those short timescale predictions, which we will actually be able to sort of like see the truth of within the next few decades. So yeah, I guess there's this distinction between ice sheet weather and ice sheet climate. Ice sheet climate being what happens over long time scales, and ice sheet weather being what happens over what's short to an ice sheet, 10 years, but long to us. And I think there's a lot of value in paleo, constraining of paleo behavior in order to kind of make statements about ice sheet climate in the future. But ice sheet weather, it's more difficult to say. But yeah, I have had it said that, like, if our models can't reproduce what happened in the past, how can they ever say what's going to happen in the future? So yeah, I think there's room for it.
Okay, thank you, Dan. And we have one more question left. So if anyone who's still with us has a burning question that you want to put to Dan, then please type it in that Q&A box. The final question that I have up on my screen is from Graham, and they are asking, might there be significant feedback between rising sea levels around Antarctica and ice shelf losses? Yes, absolutely. And that's actually an interesting question, because that's where sort of the paleo record has told us a lot. There's evidence that in the past, large sort of amounts of sea level rise have changed the sort of the position of the grounding line around Antarctica. I'm thinking of the Weddell Basin, the Weddell sector now, and it's changed the way that the ice shelves sort of interact with the bathymetry. Sort of ice rises formed and went away based on sort of Holocene sea level rise around Antarctica.
And even now, I mean, more so than sea level change, I'm losing my diction here. There's isostatic rebound going on in places, actually in the Amundsen embayment. And I don't think anyone's really looked at that yet. I think like over the past centuries, it's been constrained that like, you know, rebound rates around the Amundsen sector have been sort of like centimeters per year. And if that's the case, that could really change the location of where the ice takes hold onto the bed. And that could, I mean, if that's still going on, that could be an important thing in the future that really kind of needs to work its way into our models. And there are people within the ITGC actually working on that as well, but it's not something I've done to date.
Okay, thank you very much, Dan. We don't have any other questions to work through on YouTube or on Zoom. So that leaves me to say thank you very much for being today's MASTS webinar presenter. For anyone who is still with us and you want to recap on anything, then please check out that MASTS YouTube channel for the recording, which you can then share with anyone else as well who may be interested in today's talk. Thank you very much, Dan.
Thank you, Hannah. Sorry.
If you're still with us and you want to encounter another MASTS webinar, then we have a whole variety of talks that's still happening. Next week's talk is with Richard Lilly from Project Seagrass. His talk is titled Seagrass Restoration in Scotland, Challenges and Opportunities. All you need to do is sign up on the same sign up link that you did to join this very webinar. And we have talks throughout May as well. So if there's a topic here that you see, again, check out the MASTS website or the registration link that you used to join this very webinar, and we look forward to seeing you again. So that's everything from us this week. We hope that you can join us again in another MASTS webinar.